Welcome back. We're computing the predictive distribution for Bayesian linear regression. And we got down to this step where we're trying to get this exponent in the form of a quadratic form so that we can integrate out w. And what do we want it to look like? We want it to look like we're going to use the same trick that we used before. We want this, right? We already pulled out a -1/2. And so a Gaussian, the exponent of a multivariate Gaussian, after you pull out the -1/2, a multivariate Gaussian in W is going to be something like this. W minus a mean M, let's call it M, times a precision matrix, let's call it L. I'm thinking sort of instead of lambda, we already used lambda, times W minus M. And we multiply this out. This is just the same thing that we did in the previous, or a couple videos ago. Let's make it W transpose L. L is symmetric, so that's LM plus M transpose LM. And we would like to get this equal to this plus a constant with respect to W and Y. So this is already a constant, so we don't need to worry about that part. And we need to match these up. So let's choose. What should we choose? Let's see. Let's match this one up with this one. So we want to choose L equal to this part. Let's move the... Okay, that's fine. AXX transpose plus lambda. And let's choose... Right, we need to match this up with this. That's the linear part. So we want LM equal to this. X, Y, A. X is the vector here. Y and A are scalars. Plus lambda. Gosh, I keep writing Y from mu. Lambda mu. And we need to get M. M is the thing that we want. It's the thing we don't know. And what is M? M, well, L, for the moment, let's assume, oh, maybe we can see it directly. Well, let's assume L is invertible for the moment. Maybe we'll have to come back and check that. L, let's move to A. Since these are scalars, let's put those in front. AYX plus lambda mu. So we're going to star that, assuming L inverse exists for the moment. And now let's plug those back into this guy here. Well, I guess we don't need to plug them in, right? This was the same trick as before. Oh, wait, can we do that trick? We can't quite do the trick. We actually have to complete the square. We can't be quite so lazy as we were before, because we've got this extra AY squared out here. And also we can't be quite so lazy because this part, right? Oh, so I canceled it out, but that was a little premature. I couldn't cancel that actually. Let's rewrite that back in. Whoop. Green, because M depends on Y. So this is not a constant with respect to Y. So we can't forget about that. That's important part. Okay, so what do we get though? What do we get? Let's see. So we want to get this equal to this plus a constant in W and Y. So let's try to get that. Well, we can go ahead and plug in what we've got so far. We've got W transpose LW minus 2W transpose oh, right. So that's right. That's LM. So I guess we could just put LM here. That's probably fine. And then, is that what we want to do? LM? Yeah, I guess that's fine. That's good. And then we want to get this term so that we can factor this. We want to get this sort of factorization happening over here. So we need this guy. We've got this one, we got this one, we need this one. So add that. Oh, that's an M, not a W. Tell ya, if I get through this without making a mistake, it's going to be a miracle. Minus, we have to subtract it back off again. And then we have, right, that cancels, and then we get AY squared. So this is all separate. AY squared. Is that right? Yes. That's good. Alright, and now we can factor this guy. That's the completing the square. W minus M transpose times L times W minus M transpose LM plus AY squared. Okay. So where does that leave us? That was what we were going for. So that's looking good, and this does not depend, let's check, this does not depend on W, right? That doesn't depend on W. And M does not depend on W, so I think we're in pretty good shape to integrate to do the first step. So we're just at the first step of the process. We finally got this thing inside the integral, right? We were working with, we had the integral, we had e to this whole thing, and we were looking at the exponent after we factored out minus 1/2, and we finally got this in a form that's looking very Gaussian-like. And I think we're going to have this right here. So let's write out what we got. So we got the predictive distribution is proportional to, let's write that out. What did we get? We got the predictive distribution, probability of y given x and d, proportional to the integral e to the, boy, am I going to have space here? Minus 1/2, we have to put the minus 1/2 back. W minus M transpose L, have to make a new line, times W minus M times, continuing that line, times e to the, let's see, what's it going to be? We multiply this by minus 1/2, so that becomes plus 1/2 minus 1/2 times that. So this is plus 1/2 M transpose LM minus 1/2 AY squared dW. Okay. Now, in this, so we can, this is a normal, well, it's proportional to a normal. We can go ahead and plop in the normalizing constant for this, for the Gaussian, the Gaussian distribution over y here. It doesn't depend on, not over y, excuse me, over W. And since it doesn't depend on W or little y, just depends on this capital L, and L does not depend on little y. That's important. We can just plop that in, and we get that this is proportional to, right, it just integrates out, right? This just becomes 1. And so we're just left with what was the second part here. This is a constant with respect to W. So it just comes out of the integral. Just comes right out. And that's that function g of y, right? That's what we wanted. We had this function g of y, and now we've got it. Or that's what we wanted. We wanted g of y, and we got it. Very good. Okay, so now what? Let me think for a second here. Let's see. So where are we at? So let's go back to our plan. Our plan was, after we got g of y, Right, we wanted to get the distribution over y, so we wanted to say that it is a normal in y. So we need to rearrange this function to make it look like a normal distribution over y. And how are we going to do that? Well, we're going to do the same sort of process. We're going to complete the square. That's the only, basically the only thing that we're doing in all these calculations with these Gaussians is we're completing the square to make something look like a Gaussian distribution, and then we're either integrating it or solving for that distribution. So that's really, if there's one thing to remember about this whole process, that's it. It's completing the square. This trick that we sort of did. Okay, so now we want to get this to look like a Gaussian. So let's do the same sort of thing. So we will look at the exponent. Let's do the same. So this is going to look very similar. Let's pull out the -1/2, and let's see what we get. All right, so we're going to get, let's go ahead and move the ay squared over on the left, minus, pull out -1/2, so we get minus m transpose L m. Okay, and m is this thing. So let's work with this m transpose Lm. M transpose Lm equals, we plug in the expression for m, transpose of the product becomes the reversed product of the transposes. L is symmetric, and so L inverse is symmetric. So that's just L inverse times L inverse AYX plus lambda mu. Okay, and let's go ahead and I think we want to multiply this out. So what are we doing here? We're trying to, we want to isolate the quadratic part of y and the linear part of y from this nasty sort of big expression here. So that's what we're going to try to do here. So let's multiply this out. Well, first we can just cancel some of that. And what do we get? I guess we'll just multiply it out. AYX transpose L inverse AYX. Then let's see, this one times that one, so we get plus 2 AYX transpose L inverse lambda mu plus mu transpose lambda transpose equals lambda times L inverse lambda mu. Okay. Now we're just interested in y and y squared. And L, let's see, L, where's L? L does not depend on y. Now, L does not depend on y, and lambda does not depend on y, mu does not depend on y. So this is just a constant with respect to y. And so since this thing, all of this stuff is going to be in the exponent, then we can just forget about that part. So that's nice. And let's go ahead and write this. Let's factor out the y squared part of this. This is a squared x transpose L inverse. A and y are just scalars. Times x times y squared plus 2a x transpose L inverse lambda mu times y, just move the y over, plus a constant. Okay, out of time in this video, but we're getting close. We're hot on the trail, and we're going to get this thing. Okay, see you soon.